Today I'm going to cover a number of things that are not really difficult. Nevertheless, some of these things go unnoticed in coverage of linear programming. One of them is something you already know, how to convert different kinds of inequalities to other inequalities, or perhaps to equalities, or switches from equalities to inequalities, and also how to make the proper conversions between variables with different kinds of sign restrictions. This is something everybody, well, at least to my knowledge, you should be familiar with. Okay. The second item we want to cover, I just want to give you a graphical idea of what the possibilities could be in linear programming in terms of unique optimal, no optimal solution, sometimes no feasible solution, etc. Okay, let's just get the pictorial idea. And after that, we'll talk about the so-called requirements space interpretation of linear programming problems, which is covered also in your book by Bazara, Jarvis, and Sherali, but typically not covered in many other textbooks. Okay. And the last item, time permitting, is the Fourier-Motzkin elimination, which typically goes unnoticed in linear programming, even though Danzig, for example, in his initial book on linear programming and extensions, had a section on Fourier-Motzkin elimination, which is a way of solving linear inequality systems. Anyway, you might be familiar with some of this or may not be, but these are small items, or at least items that do not require too extensive knowledge. Nevertheless, it's good for you to have some idea of what these things are. Let's just talk about the conversions between different kinds of inequalities. Or different kinds of functional constraints. So the first thing you might want to do is to convert a less than or equal to type of constraint into a greater or equal type of constraint, and that's easy to do. All you have to do is, if your ith constraint is of this form, AI is a row vector of, say, n elements. You've got x column vector. It's got n elements in it, the xj's 1 through n. And if this is the constraint and the consideration, and if you want to convert that to the other form, all you have to do is multiply by -1 both sides, and it's done. So you will have minus AI on the left times x greater or equal minus BI on the right side. That's easy. Number two is, of course, quite similar. You want to change a greater or equal type constraint. Again, through multiplication by -1, you get the reverse inequality. That's straightforward. Number three, we may wish to convert a less than or equal to type constraint into a equality type constraint. In this case, if you've got, for example, AIX less than or equal to BI as your ith constraint, all you have to do is you define a new variable. Let's just call it, say, SI. People refer to that as a slack variable. You define that. That means, by definition, to be the difference of the larger side minus the smaller side. So in this case, it will be BI minus AIX. Why did I choose this to be the difference of the larger minus the smaller side? Because XSI, I want that to be greater or equal to 0 in the typical case in standard form problems. So when you do this, now you have a new problem with AIX plus SI being equal to BI. That's what that definition tells you, actually. Plus, because of my definition of the slack variable, it needs to be greater or equal 0 if I want to force it to be non-negative. Okay? So that's something you already know. Number 4, similar situation, except that we have now a greater or equal type constraint, and you want to make it equality. In that case, you've got AIX greater or equal BI, and you define, again, a variable SI. In this case, it's called an excess variable, or some people refer to it as a surplus variable. And that's, again, in this case, AIX minus BI. That's the intended meaning of that variable. So that your constraint now becomes AIX minus SI equals BI with SI restricted to non-negative variables. So these two constraints do the job. They actually enforce the intended definition of the variable. Number 5. You might want to switch from equality to maybe inequality, but you cannot do it with a single inequality. You have to use a pair of inequalities in that case, because if AIX is equal to BI, it must necessarily be the case that AIX is less than or equal to BI, as well as AIX is greater than or equal to BI. And if your X vector satisfies both inequalities, of course, it must equal BI. What else can you think of? Well, these are the only things I can think of. If you come up with something more, then we'll handle that as well. Let's also talk about conversion of variables, conversion from one type of sign restriction to another type of sign restriction. In this case, of course, I'm just going to deal with common cases. If you have a variable, say xj, which is supposed to be non-positive rather than non-negative, and you typically want your variables to be non-negative in most cases. So to handle this, all you have to do is you define a new variable which is the negative of the old variable, which means that in the constraints you are using the same columns. That's the first column of the A matrix, or the multiplier for the x1 variable, except that the jth column becomes the negative of what you want. So for the jth column, you have the negative of the old column times xj prime, because now xj prime stands for the negative of xj. Okay? Plus the last, up to the last one. So the other ones don't change. This is the only one that changes here. And then, of course, the right-hand side could be any of these things, equal to, less than or equal to, or greater than or equal to b. Okay? I don't have space, but this goes here, of course. Okay? By the way, in the objective function, if you have a cost Cj for xj, now you replace that with negative Cj, so that the multiplier, the cost in front of xj prime, is certainly the negative of the old cost. Okay? So all we're doing is we're substituting minus xj prime wherever we see xj. That's all we're doing. But that changes the problem data. The column becomes the negative of the old column, and the cost becomes the negative of the old cost. Number 2, you have a variable which is unrestricted in sign, URS, as many students like to write. If this is unrestricted, you define it to be the difference of two non-negative variables. So you put xj prime minus xj double prime with the additional constraints, xj prime and double prime non-negative. Okay? In which case, of course, the aj xj in the constraint matrix becomes aj prime xj, sorry, not aj prime, aj xj, not, there's no prime, minus aj xj double prime. This one has a prime. I just misplaced the prime actually. aj xj prime minus aj xj double prime. That's what you substitute in the constraint matrix. And in the cost, in the objective function, cj xj is now cj xj prime minus cj xj double prime. So you've got one additional variable in the problem, and that introduces an additional column as well as an additional cost or contribution in the objective function. Okay, so this is simple stuff. I'm sure many of you are already familiar. If you're not familiar, you work out some numerical examples to get yourself quite familiar with these conversions. What was the second thing I wanted to talk about? The possibilities. Okay. There are many possibilities, and in two-dimensional pictures, if you have a feasible region that may look like, for example, like this, with functional constraints as well as non-negativity, the inside of this is your feasible region. We had an example at the very beginning, so I assume you can construct such feasible regions in two dimensions if you have only two variables. So in such a situation, if your cost vector C points, for example, in that direction, then moving along the cost vector will get you larger and larger. So movement along the C direction is a maximum ascent direction. Okay? Any movement within 90 degrees, strictly 90 degrees of the C vector will also increase your objective value, but not as fast as the movement along the C direction. These are things you might want to try out at home on your own. Anyway, if you look at the contours of the objective function, for fixed z value, the z is the objective function value, for fixed z, so we're looking at the problem of the following kind. Okay? For fixed z, the contours will go parallel and perpendicular to the c vector all the time. And in this picture, it turns out that that's the largest you can get, because any further movement will take you outside of the feasible region. You should slice at least one feasible point to be able to realize or to be able to attain an optimal value. So that's the optimum point, and in this case, it's the unique optimum point. Okay? According to this picture. Now, of course, we have other possibilities for the same feasible region. My cost vector may point like this, in which case my contours will go, let me just change the picture a little bit so I get what I want. So it goes like this, and finally it actually coincides with one of the edges of the feasible region or one of the, and in this case, of course, everything here is optimum. So this is the set of optima. You've got multiple optimum solutions. All right. You may have the same situation with unbounded feasible regions. In this case, my feasible region is here. In this case, the feasible region is bounded, meaning that it's contained in a or within a sphere of finite radius in that dimension. Whereas in this case, regardless of how large a sphere you choose, sphere in this case is of course a disk, okay? You won't be able to contain the entire feasible region. It just goes all the way to the right. So in this case, if I have a C vector that points like this, my contours will go something like this. Okay, I chose the wrong one. It's almost parallel. Anyway, let's just make the alternate optima first. Okay? And this one will coincide with the edge that extends from this corner point to the all the way to infinity. So in this case, the set of optima is here. Okay, on that edge, on that ray. That's not an edge because it extends all the way to the right. All right, so alternate optima, alternate optima. Of course, you could also have the situation where you have a unique optimum if your C is like this. In this case, you have a unique optimum, even though your feasible set is unbounded. My pictures are a little bit sloppy, but nevertheless, you get the idea. Okay? If you have an unbounded solution space, in other words, it cannot be contained in a sphere of finite radius, and if your objective function for maximization has a cost vector that points, for example, as in this case, then your contours will go like that. And regardless of how far to the right you move, you get larger and larger values for your objective function. Nevertheless, for each fixed value of z, you can still slice through the feasible region, which means you can always attain that particular objective value by means of certain feasible solutions. That happens to be along the line, along the portion of the contour line in that corresponding to that particular z value. Okay, so this is the case of unbounded solution or unbounded linear program. Okay? In such a case, we may use the terminology z is actually infinity. We may just adopt that convention, even though I don't typically like such things. We may just, for unbounded linear programs, we may just call z to be infinite in value. That's what your second book does, the second recommended book. So I'm just going to adopt that also. What is the last possibility? The last possibility is you may have constraints that are in conflict. Okay? Some of the constraints contradict other constraints, so you have no feasible region. For example, you might have a constraint like that, another constraint that tells you to go this way. In this case, if you wanted to satisfy non-negativity relative to that constraint, you want to be here in this portion, but then it does not agree with the sense of the constraint in the bottom part, that one. Otherwise, you might want to be here, but in which case you don't, of course, satisfy this upper constraint. So this is the case of no feasible solution. Okay? Nothing new so far for many of you. Nevertheless, this is at least some snapshot of what possibilities may arise. All right, so let me continue with the requirements space. Suppose I have a linear program in m variables, and the constraints are equalities. B is a vector of 2 dimensions because it doesn't have to be, but nevertheless I'm going to assume it to be small dimensional so I can illustrate what's going on with this problem. A1 is the first column associated with the first variable, so on and so forth. So AJ's and B are of the same dimension. And let's assume, let me see if I have any other constraint here. Yeah, X is also non-negative as a vector, okay? Now, in this problem, if you wanted to simply interpret feasibility, forget the optimality first, okay? In this case, let's assume my AI or AJ are, say, in m-dimensional space, and B is also in m-dimensional space. All you're doing, say, for the case of 2 dimensions, is you're taking the first column, say this one, whatever it is, this is the origin, that's the point where that particular column represents. You take the second column, which could be this one. You take the third column, which could be this one. You take the fourth column, which could be that one, so on and so forth. And assume in this case we've got, say, 4 columns like that, okay? Now, this equation tells you that I want to multiply my column vectors with non-negative numbers, add them up, and get the right-hand side vector B, okay? So that will only be possible if B belongs to the cone that you see here. That's the non-negative cone that can be generated. Any point in this cone can be generated by taking non-negative multipliers for each of these vectors. Okay? All right, so to have a feasible solution, feasible solutions are possible if B is in the cone, in the non-negative cone generated by A1 through AN. Let's make it convex cone rather than cone, because cones are like this. They include both sides. But I just want to take one portion of the cone, which is generated by the non-negative numbers, xj's. So let's call it convex cone. Okay? C stands for convex here. You don't know the definition of that. Nevertheless, just keep the picture in mind. it'll be clear when we start talking about convexity later. All right. So in this case, if, for example, B is this vector, this one has a feasible solution because obviously I can choose non-negative multipliers for A1, A2, A3, A4 so that B is expressed as a sum on the left. Okay? Whereas if the picture is a little bit different, this is the convex cone, A1, A2, A3, A4. And if my B is, for example, pointing this way, then there's no feasible solution. You cannot express B as a non-negative linear combination of these vectors. No feasible solution. Of course, the pictures are, we can draw the pictures only in 2 dimensions or also in 3 dimensions if we try a little bit harder. Nevertheless, these ideas are actually valid for any dimensions m and n, okay, in the column space as well as in the row space. Okay? So, this statement, for example, is true regardless of what m is and what n is. Okay? M is the number of constraints or the dimension of the columns AJ as well as B. N is the number of variables, x1 through x4 in this example. Okay? Any other questions? Okay. Now, if you wanted to interpret optimality in this case, it will be the following. So let's just try. Optimality for the same type of problem with equality in the constraints and non-negativity. So in this case, I have one more linear expression whose right-hand side is a z. It's a variable number. I'm trying to maximize z here. Okay? I just define z to be the output value from the objective function expressed in this way. And then we also have the columns for which the B vector is a fixed vector. Z is a variable number. Okay? Nevertheless, you may pretend that you know the value of z and just assume that it's tentatively fixed. It could be fixed, of course, to different values. And then, additionally, we have non-negativity. So, in this case, suppose my convex cone generated by the columns A1 through AN are, it's this cone, whatever. Let's just take this to be the cone. As in the previous example. Now, I'm assuming in this case A1 through AN and B are one-dimensional, just for the purposes of the picture. Does that make sense? Let me see. Okay, so let's make this the column vector C1, A1. Okay, just a second. Let me just check that. Yeah, okay. Let's just assume this is C1A1, this is C3A3, C4A4, and this one is C2A2. So I'm assuming A1, A2, A3, A4, they are one-dimensional, and when you take them together with your CJs, then they will become two-dimensional. That's the only purpose for that assumption, is I want to be able to illustrate what's going on here. All right, these are the vectors defined by CJ, AJ, for J going from 1 up to 4 in this case. Okay. Now, what are we trying to do? For fixed Z, we want the vectors Z and B to be in the convex cone of these vectors. So you want, for fixed Z, you want Z and B as a vector to be in this convex cone generated by these vectors. But meanwhile, you also want to maximize Z. Now, B is, by assumption, a single-dimensional vector. So for fixed Z, I can take, for example, the vector. Let me make that in different color. That's a point obtained by a fixed value, say Z1 and B. Okay, Z1 is a number, B is just a number in this case, because we're talking about one-dimensional. Now, if I wanted to make Z larger and get another point here, for example, this will be Z2MB, right? Can you see that? Let me make that more legible. All right, they are at the same height relative to the horizontal axis. Okay, there's a horizontal axis here, there's a vertical axis. Why are they in the same height? Because the Z1 value, if you imagine a axis here and another axis here, the Z1 value is here, the Z2 value is here, right? And this is the B value. B is just a number in this case, okay? So you can see that when you start playing with Z, you're generating all these points here. All at the same height, all at the same B value. So anyway, you've got all of these things. Now, what do you want? You want whatever Z value you pick, you want ZB to be within the cone. So in this case, since you're trying to maximize Z, what is the point of exit? The point of exit is this point here. That's the largest you can get to be and still stay within the cone. So that is your optimal Z, let's call it Z star, the optimal value, whatever it is, I don't know, and B, okay? And pictorially, at least you can envision what's going on here. If I don't give you a numerical example, I guess things may be a little bit confusing. So let me see. I did, in the past, work out a numerical example for this thing. It's a simple one, so let's just look at that. Except that, okay, yeah. Here's a numerical example. I've got maximize x1 minus x2 subject to minus x1 plus 2x2 less than or equal to 0, and minus 3x1 plus x2 greater or equal minus 3 with non-negative restrictions on both variables. Now, this problem is not in the form I wanted because I assumed equality is there. Okay? Nevertheless, you can plot this, by the way, in the x1, x2 space and see what's going on. This is a two-dimensional example in the x1, x2 variable in the space of variables, and we did that already in the first lecture, and you can do it on your own. You've got only four constraints and two variables. Now, when you look at the requirement space, I need to first change this to equalities. So I'm going to do that by introducing a new variable x3, which is a slack variable, and a new variable x4, which is a surplus variable. So you've got that, okay? With x1, x2, x3, x4, non-negative. All right. So,
minus 6.
Pardon?
Minus 6.
Yes, that's a minus. Thank you. And the objective function is still the maximization. Let's also take z to be the value of the objective function. x1 minus x2. By the way, slacks and surplus variables, they don't contribute anything to the objective function. They simply absorb the excess amount or the deficient amount in the constraints, so they don't change the objective function. All right, so in this case, this is the situation. My A1 vector is minus 1, minus 3. My A2 is 2, 1. I'm just picking up the coefficients. A3 is 1, 0. A4 is 0, minus 1. These are the vectors. And the B vector is, as you see, 0, minus 3. Okay? So the question is B in the convex cone of these vectors? Well, let's just plot them and see. Minus 1, if I assume this to be the origin, minus 1 and minus 3, let me do it here. Minus 1 this way, minus 3 that way. So this is my first vector. Okay? My second vector, 2, 1. So I go 2 units, which is essentially here, and then 1 unit. That's 2, 1. Then we have 1, 0, which is this one. And then we have 0, minus 1, which goes down. Okay? So my convex cone is what I see here. Okay? And where's my B? It's 0, minus 3. 0 and minus 3 is all the way down here. So there's a feasible solution because B is inside the convex cone of these column vectors. Okay. if you wanted to interpret this without the equalities, how would you do it? Does anybody have any idea on that? Suppose I just wanted to analyze the situation with respect to the inequalities rather than changing them into equalities. Okay. In that case, all we have to do is to reinterpret the situation. I'm going to come back to the optimality stuff if time permits, but let's just look at the inequality situation first. So if your problem is in the following form, rather than equality, you would still be looking at your different vectors and generate the convex cone. Suppose this is the situation. That's the convex cone we're talking about. Okay. Now the B vector, when you take a typical B, for example, if you take B here, that's a vector, that's a point. You want numbers generated on the left to be less than or equal to B, which means that if you look at this if you look at this hyperrectangle, except that two sides are removed, okay, you want to be in the red region. All points in the red region are points whose each component is less than or equal to the corresponding component of the B vector. Okay? Everybody sees that, I hope. All right. So, in this case, since the red region intersects the convex cone of the AJs, obviously there's a feasible solution because any point inside the intersection will do the job. When you choose xj's accordingly, you will be able to generate a feasible solution. So in this case, you want, for feasibility, requires that the convex cone of A1 through AN have a non-empty intersection with the set of points y in Rn, where y is less than or equal to b as a vector, or each component of y is less than or equal to the corresponding component of b. B is a fixed vector, y is just collecting such points. Okay? This is the red region. The red set in the picture. Okay? The other one is, of course, the black one in the picture. So as long as this intersection is non-empty, we have a feasible solution. And in this case, of course, the red-colored B induces a feasible solution, whereas if your pictures were a little bit different, if the cone is like this, and if your B is, for example, pointing this way, so this is your B, In this case, there's no intersection between the red region and the black regions. Okay? So there's no feasible solution here. Okay, in the remaining few minutes, let's just look at the optimality business, which I'm going to do here. This is a numerical example which is different from the one we had because I want one-dimensional vectors at the in the constraints. So I have a single constraint here, x1 plus 2x2 less than or equal to 2. That's my constraint. Okay. So the way we want to interpret this problem is to maximize z subject to 2x1 plus 3x2 equals z on the right, which gives you the following vector equation. 2 and 1 for x1, 2 and 1. Okay? Plus. The second column will be 3 and 2. For the second column. And then if I'm going to use equality, I assume, well, you just introduce a slack here, introduce x3 with non-negativity, in which case the objective or the cost coefficient is 0, and it has a 1 in the constraint. That's your x3. And the right side is z and 2. And you want variables to be non-negative. All your variables are non-negative. Okay? Okay. Now I can certainly plot these vectors in the two-dimensional plane. So 2 and 1, if this is my origin, I go 2 units and 1 unit somewhere here. That's 2, 1. The second one is 3, 2. So we go 3 units here, 2 units this way. I don't know if that's 2 units. Anyway, I'm doing this approximately. That's your 3, 2. And you've got 0, 1. So 0 and 1, which is this point. So my cone, in this case, is what I see here. Okay? Now, if you look at the vector z and 2, for example, when z is 0, you have 2 here, which is at the same height as that one. And then, of course, when you keep the second component fixed but change z, you start generating this line here. Let's make it broken and outside of the feasible region. So since we're trying to maximize z, this corresponds to z of, so this is for z equals 0, and that's going to be your optimum z. So that's going to be your z star and 2. Okay? Whatever it is, you can compute that. It's a multiple of this 2, 1. So you can compute that. How much is that? It'll be 4, I guess. 2, 1 and 4, 2. Yeah, this should be 4. Just by inspection. I don't know. if that's really the situation. Yes, it is 4. Okay. Okay, let's stop here. There was no time to get into the Fourier Motzkin elimination. We'll pick it up perhaps next time. Okay.